Good evening, and welcome to Kent County SKYWARN Basic Radar Training. My name is Colin McConkey, and my amateur radio call sign is KE8RXN. And this evening, over the next span of an hour or so, we're going to look together at basic radar training, specifically in relationship to Kent County, Michigan SKYWARN operations. But I will say, perhaps you're watching this video on YouTube after the fact and you have no idea what Skywarn is. Perhaps you've never looked at radar beyond simply looking at a mobile weather app on your smartphone. We're going to cover all of that to hopefully provide a good foundation upon which we can build later on in this video and also in subsequent radar videos to more advanced skill sets that you can use not only for your personal weather preparedness, but also in service of Skywarn, whether it be in your local county area, wherever you live, or here in Kent County, specifically for those of us who are trained National Weather Service Skywarn spotters, as well as licensed amateur radio operators. So, first of all, for those of you who both do and do not know me, for both groups of folks, who exactly am I? A bit of an introduction of myself. Well, my name is Colin McConkey. Again, my amateur radio call sign is KE8RXN. And I became licensed as a technician class operator back in April of 2021. I was a COVID ham, as it was. I earned my amateur radio license due in part to wanting to be more prepared in light of all of the disruptions that the COVID-19 global pandemic was causing, not only in terms of health impacts, but in all sorts of impacts, such as with supply chains, communications, and so on and so forth. In May of 2021, I upgraded to a general class license, and finally in July of 2021, I upgraded to the highest level of amateur radio license currently offered by the FCC, which is Amateur Extra, or more commonly referred to simply as Extra. Not only am I an extra class ham radio operator, I am also currently, particularly as of this year at time of recording in 2023, the assistant team leader for Kent County SKYWARN. And the assistant team leader serves underneath the leadership of the team leader for Kent County SKYWARN. We'll get into more of that later, what all SKYWARN entails and so on and so forth. But my own personal interest in weather was sparked all the way back in May of 2013, almost a decade ago, actually, with the El Reno, Oklahoma tornado. Now, this fascinated me for two particular reasons. One, I've always had a general interest in tornadoes. After all, they are among the most terrifying and most destructive localized severe weather events on planet Earth, only to be rivaled by more widespread severe weather events such as hurricanes, tsunamis, earthquakes, and so forth. But also because it produced and still stands to this day, a decade later, the highest measured wind speeds in the history of planet Earth at 306 miles per hour, as measured about 100 feet up into the supercell that day by a mobile radar station, as the details are, as I recollect the details in my own memory. So between 2013 and 2021, I had an off and on interest with severe weather and tornadoes and so forth. I would watch tornado documentaries. I've detailed that elsewhere. If you look at my other videos on my YouTube channel, specifically for Kent County SKYWARN tornado training. But in 2021, when I became licensed, my primary goal for amateur radio, as previously stated, was not only for personal preparedness and family preparedness and emergency communications, but I knew immediately that I wanted to dive more into my burgeoning interest in weather, which had been peaked, but also at the same time somewhat latent for the 8 years since 2013 at that particular point in time. So in 2021, I joined the Kent County SKYWARN team. In 2021, I focused primarily on learning more about radar observation and analysis, and I primarily served the team in that role. In 2022, I took on additional responsibilities by studying as deeply as I could, taking classes that were offered to professionals. I myself, of course, not being a professional National Weather Service meteorologist or forecaster, simply an amateur weather enthusiast who is a trained SKYWARN spotter, currently the assistant team leader for SKYWARN operations in our county. I studied as much as I could and still continue to do so to this day about forecasting and the science of meteorology, and I would produce forecasts for our team, which, as I will leave for others to judge, I believe were able to aid in our SKYWARN operations, particularly when it came time to activate. But certainly that was not just due to my own efforts, that was because of the fantastic team that we have and also the team leader that we have as well. So now this year, I take on added responsibilities as the assistant team leader for volunteers for National Weather Services here in Grand Rapids, Michigan, as well as Kent County Emergency Management. And I will quickly say, in case you are not local here to the Kent County area or to West Michigan, perhaps you are a resident in a different state or perhaps even a citizen of another country listening to this radar training. Kent County is located in the western half of the Lower Peninsula of the state of Michigan, and we are the second largest county by population. In the center of our county lies the city of Grand Rapids, and that is the second largest city in the state of Michigan currently, second to Detroit, which is known around the world, of course. But it is very necessary for us to have a very good team of SKYWARN spotters, radar analysts, forecasters, and so forth, precisely because we service so many people in our county, the second highest populated county throughout our entire state. And so that is a bit of a personal introduction about me, but we don't want to talk about myself for too long because what we want to cover is the basics of radar. So what we're going to do this evening is we're going to look at together the history of the National Weather Service and radar, albeit a very brief overview. And then we will look at two of what we call the most common products. In other words, the images generated by radar, specifically reflectivity and velocity. And doubtless many of you watching and listening to this will know already what those are, but nevertheless, for those of you who are not familiar, we will cover those two products in detail, and I will hopefully explain that all clearly later on this evening. We will also briefly look at radar software options that are currently on the market, and in subsequent videos, I intend to dive more deeply into other radar softwares that I highly recommend for all SKYWARN spotters to use. But the second half of this presentation will conclude it by looking at a live demonstration of the GR Level 3 radar software. And I will walk you through recommended setups as recommended from various levels of leadership and competency in terms of our policies, and also what local meteorologists from the National Weather Service here in Grand Rapids recommends, and also combined with my own preferences, and I will illustrate my preferences with reasons why I think it prudent to set them as they are. But there is certainly room for experimentation, and there are certain things that I do not recommend that you set or fail to set in GR Level 3, but there are other things which I will cover later throughout this presentation that you are more than welcome to set to your own personal preference, and you are free to experiment with it as you wish. So, before we go to the GR Level 3 live demo, let's first get an understanding of radar. And in order to do that, we have to look at the history of radar. And the history of radar really goes back to the history of radio waves, that is, the discovery of radio waves themselves, all the way back in the late 19th century. In the year 1886, a physicist by the name of Heinrich Hertz observed that objects reflected electromagnetic waves. But he also observed that these electromagnetic waves not only bounced off objects, but you could also direct, just as you could with a visible beam of light, these electromagnetic waves into specific beams of various strengths. Now, for those of us who are ham radio operators, obviously his last name of Hertz immediately stands out to us because we measure radio waves in terms of hertz or 1 cycle per second. For example, our local SKYWARN repeater frequency is in 145.270 megahertz, or 145,270,000 megahertz. So, very many cycles per second indeed. But he observed, just to reiterate, two things: that you could reflect electromagnetic waves, which is quite simply a radio wave, as you can see in the lower right-hand corner of the slide deck here, with the vertical electrical field component and the horizontal magnetic field component. He observed not only do radio waves bounce off objects, as light will reflect off an object, but that you could direct radio waves into beams, just as you could with visible light. And we know this not only intuitively from experiences with visible light, which is simply, I might add, a radio wave in the terahertz section of the radio spectrum. And if you're uncertain as to what a terahertz is, it's simply a radio wave that is uh, oscillating at an extremely high frequency, so fast, in fact, that you can actually see it. And that is the basis for visible light. But not only do we know it from the visible light spectrum, we also can hear it as well in the acoustical spectrum. That is the frequency ranges that human ears can generally hear, which, depending on the quality of one's hearing, will generally range from about 20 hertz up to about 20 kilohertz or 20,000 hertz, which are certainly well below the frequencies for radio waves themselves. But I don't want to dive too much into the science behind radio waves, because that is an excellent example of why, if you are unfamiliar, I would highly recommend you study for your amateur radio license exam. So moving forward approximately 20 years, 18 to be precise, in the year 1904, a German engineer was granted a patent in using radio waves, that is electromagnetic waves, to detect obstacles for the purpose of aiding maritime navigation. Obviously, mariners, both then and now, need to dodge obstacles that they would encounter throughout their navigational experiences. And so a German engineer was granted a patent in the early 20th century in 1904 to try and develop a system to aid mariners in detecting things such as reefs and so forth, or in coastlines and all that, so they would not run aground and possibly risk damaging their ship, losing their cargo, or in worst cases, putting lives at risk. About 20 years later from that, another 18 years actually, to be precise, in 1922, up through the end of World War II, scientists would use this technology of bouncing radio waves off objects and directing them into beams to detect enemy ships. Obviously, aviation was around in a very limited capacity in World War I, but particularly became much more lethal in World War II. And in World War II, radar technology was used in order to try and detect enemy aircraft, as well as enemy ships as well. I will quickly add that for those of you who are familiar with sonar technology that was developed by the United States in order to primarily detect German U-boats in World War II, it's basically the same context as radar. It just operates in a liquid medium rather than in, to be technically precise, another liquid medium, but we don't typically think of the atmosphere as a liquid, even though that is in fact what it technically is. But nevertheless, radar and sonar are inextricably linked with each other, for they are indeed the same technology. So as we move further in history, one of the things that radar observers had found, and in the top right corner of the slide deck, you can see two engineers working on a World War II radar station at the time. They found that precipitation, in other words, rain, snow, sleet, hail, and so on and so forth, would generate false positives on radar when attempting to detect enemy aircraft. They already knew that they could bounce radio waves off objects in the atmosphere, and they intended to only do so in order to detect enemy aircraft. But accidentally, which proved to be very fortuitous for weather observation approximately 100 years later to this day, they found that enemy aircraft, along with precipitation, would generate radar returns, or echoes. In the same way that you might not expect to hear an echo, they did not expect to see these radio waves echoed back to them off precipitation, these water objects in the atmosphere. And so the United States Navy and the United States Air Force continued to develop radar technology throughout the decades of the 50s and the 60s, which would eventually be adopted from the military by the National Weather Service. Now, as we will cover here shortly, it was not then known as the National Weather Service, but many of the original radars that were first on used by the National Weather Service were actually repurposed wartime radar equipment. And nowadays, as we will cover here on the next slide, and as you can see with a picture of the local radar site here in Grand Rapids, Michigan, in the lower right corner of the slide, radars today primarily serve the purpose for weather forecasters in the National Weather Service. Of course, military still uses radar very much to this day. Aircraft controllers still use radar as well to detect aircraft to make sure that flights can arrive and depart safely and securely from various airports. But when we move into the decades of the 80s, specifically in 1998, NEXRAD, or Next Generation Radar, was developed due to a joint effort by the Departments of Defense, the Departments of Commerce, and the Departments of Transportation. And a few years later, by the early 90s, Next Generation, or NEXRAD, radar stations covered the United States, and these are still very much in use to this present day. For those of us who are ham radio operators, we would be interested in knowing that NEXRAD radar primarily utilizes, to the best of my research, but you would need to confirm with your local engineers at the various radar locations as served by the nearest National Weather Service office in relationship to your location. NEXRAD radar primarily utilizes the 10 centimeter band, which is more commonly just known as the S band. And this is used today by air traffic controllers, weather stations. It's also used in some applications by NASA, as well as other purposes. And it's the 10 centimeter band, which, if we translate that into frequency rather than wavelength, is approximately 3 gigahertz. And it's in the upper UHF, or the upper ultra high frequency portion of the radio spectrum. The radar software that I will demo here in the second half of this presentation, GR Level 3, utilizes this NEXRAD radar data. And you can also, if you're interested, in some cases, various radar programs will allow you to do it natively from within the application itself. You can download historical radar archives from NOAA's National Centers for Environmental Information. NOAA standing for the National Oceanic and Atmospheric Administration. So that briefly covers the history of radar, but now let's also quickly talk about the history of the National Weather Service, because obviously as Kent County SKYWARN spotters, we particularly use our radar observational skills to alert us to potentially severe or confirmed severe weather conditions that we can then report to the National Weather Service in order to aid them in issuing the appropriate products that they have the authority and the knowledge to issue as conditions dictate. So let's also quickly cover a history of the NWS, or the National Weather Service. And again, that takes us back to the early days of our country, even further than the late 19th century. We have to go all the way back actually to the late 17th century. Weather observation and weather spotting has been integral to American history since our nation's founding. If you look at, for example, the personal biographies and histories of men such as George Washington, Thomas Jefferson, they would routinely pay very close attention and report the conditions of the weather around them. In fact, a young man who was named Alexander Hamilton, who of course would play a remarkable role in American history, wrote to a relative about the horrific experiences that he endured during a very powerful hurricane that hit the east coast of the United States during his younger years. And he talked about the utter devastation that was unleashed by the powerful hurricane, and the families and the individuals who had just roamed the streets with completely flattened structures with nowhere to turn for help. And that memory was seared into his consciousness throughout his life. Back then, of course, they had very little in the way of anticipating something such as a hurricane. But nevertheless, people even then knew just how vital severe weather was in terms of trying to prepare for it and avoid the effects from it, if at all possible. So from the time of our nation's founding, from the time of the founding fathers, up until right before the Civil War, The Smithsonian Institute would receive reports from weather spotters throughout the United States, and they would use these to create weather maps. At the time, the technology they used to communicate this information was the telegraph, but they would create weather maps based on spotter data that was reported to them throughout the Civil War. Now, 5 years after the Civil War ended, President Ulysses Grant, obviously the former victorious Union general, when he was duly elected president, he signed a law on February 9th of 1870 that would create a national weather service. And 20 years later, this would become formalized into what was the predecessor to the NWS, and it would be known as the U.S. Weather Bureau. And it would have the title the U.S. Weather Bureau for approximately the next 80 years or so. And it's interesting, you will sometimes hear older Skywarn team members or ham radio operators still refer to the National Weather Service as the U.S. Weather Bureau, even though it's been 53 years since the NWS has been called the U.S. Weather Bureau. But back in the end of the 19th century, around the time that the rudimentary understandings of radio waves were being developed, the U.S. Weather Bureau was first under the direction of the Department of Agriculture. And by the year 1900, at the dawn of the 20th century, the Weather Bureau forecasted weather and issued weather warnings to alert the public to impending severe weather. And we can see, even in the earliest 20th century, such as in the movie The Wizard of Oz, where the tornado comes and destroys Dorothy's home, we can see a fascination in the American consciousness with severe weather at that time. There was actually a time where weather forecasters with the Weather Bureau were barred from using the term tornado for fear of inciting mass panic at the time, because there was such a fear of the destructive and at that point relatively unpredictable time frame of tornadoes. Nowadays, of course, we have much better tools and lead times thanks to the wonderful work of the professionals such as our local National Weather Service offices, but also the Storm Prediction Center and all of the supercomputer models and so on and so forth. Back then, of course, in the year 1900, leading into the year 1940, they did not have that technology or knowledge readily available at that time. So in 1940, the Department of Commerce would take over the Weather Bureau from the Department of Agriculture, and 8 years later, in 1948, 3 years after the conclusion of the Second World War, United States Air Force meteorologists would issue an historic weather warning product, and that simply was the first tornado warning was issued in the year 1948 from Tinker Air Force Base in the state of Oklahoma. And it's an interesting historical fact that the Storm Prediction Center, now based in Norman, Oklahoma, would be located near the modern day Tinker Air Force Base. The Tinker Air Force Base was not the actual predecessor to the Storm Prediction Center, as it's still a military base to this day, to the best of my knowledge. But it is nevertheless interesting that that is where the first tornado warning was issued. As we get into the mid 1960s, in the year 1965, the Department of Commerce would create the Environmental Science Services Administration, and this would take ownership of the U.S. Weather Bureau. So you can see that the U.S. Weather Bureau has bounced around throughout its history, even prior to it becoming known as the National Weather Service, from various cabinet departments and executive agencies. 5 years later, in the year 1970, the U.S. Weather Bureau would become the National Oceanic and Atmospheric Administration, or what we more commonly refer to as NOAA in the present day. And not only at that time, but it would also become known, the Weather Bureau would become officially known in the year 1970 as the National Weather Service. 19 years later, of course, radar had already been utilized by that time, but in the year 1989, Congress and the president knew that there had to be a plan to modernize National Weather Service radars. So in 1989, a 10-year, $4.5 billion plan was approved and voted on and got underway to modernize the National Weather Service, among the most important features of which was the implementation of NextRad, or Next Generation Radar, stations throughout the United States. And these stations are still in use today. They are often upgraded, they are often repaired. A couple years ago, our radar station in the National Weather Service in Grand Rapids, Michigan was offline for a while because they were upgrading it. In fact, that may have been early last year, come to think of it. Time is still a the passing of time is still a bit of an odd thing to experience in a post-COVID world, but I digress with that. In service still today are these next generation radar stations throughout the United States. And if we quickly look at the history of the National Weather Service office here in Grand Rapids, Michigan, when we look 120 years ago, in the year 1903, the U.S. Weather Bureau, as it was then known at the time, established a weather forecast office, or a WFO, a weather forecast office here in Grand Rapids, Michigan. And 31 years later, in the year 1934, an airport was created, or rather, an airport office was created adjacent to the Kent County Airport, as it was then known. Now, today, the National Weather Service GRR office still operates physically adjacent to the Gerald R. Ford International Airport. And as a personal anecdote, I was honored to have been at the uh, commemoration and the inaugural ceremony, the dedication, that's the word I'm looking for, of the former Kent County Airport to the Gerald R. Ford International Airport by President Ford when he was still alive. There was obviously a news release to the general public, and they were invited, and we were able to attend. And he is still to this day the only United States president that I have seen in person, but I digress. Nevertheless, the National Weather Service office still operates today adjacent to the Gerald R. Ford International Airport here in Grand Rapids. And that is something that you will commonly see a pattern of throughout the United States. Major airports and WFOs, weather forecasting offices, are often placed next to major airport locations. In some cases, the largest airports throughout the United States have their own dedicated radar sites. And we can look at that once we get to the live demo of GR Level 3. But that covers a brief overview of the history of radar and the history of the National Weather Service, on behalf of which we as trained SKYWARN spotters volunteer our time and resources to give the most accurate ground truth that we possibly can. So, how do we do that? How do we know what type of weather is approaching us? And if we are physically located in the path of the most likeliest form of severe weather in our local area, to be on the lookout for certain severe weather criteria? We do so by using radar. So turning now to the first in a series of two products on radar, we're going to talk now about radar reflectivity. And thankfully, this is going to be the most intuitive for anyone who has ever seen a radar image at any course of their lives. It is radar reflectivity, which is the most commonly distributed product from next generation radar stations throughout the United States. And if you look at the background of this particular title slide here, reflectivity would be in the upper left quadrant of this particular screen. The blues, the greens, the yellows, and the reds. I'll talk later as to why I don't recommend you refer to reflectivity in terms of colors on air during SKYWARN operations, but we'll get to that. Nevertheless, for those of us who have seen a radar image, we intuitively know, even though perhaps we've never thought of it in such terms, what reflectivity is. And again, if we think all the way back to the experiments in the late 19th century, reflectivity is simply the concept that you can bounce a radio wave off objects suspended in the atmosphere and have them return to you. And you can also direct those radio waves into beams. That's exactly what reflectivity is. Just as you can reflect light off a reflective surface, just as you can hear yourself echo in a room with the acoustic properties that will return that sound wave to your hearing, reflectivity is the echo of the radar's electromagnetic beam. It's the echo of the radar's radio wave, the pulse being generated by the radar. The radar will send out a beam of electromagnetic particles. Those will encounter objects in the atmosphere and return to the radar, and then the radar will interpret that reflected data and produce the radar images that we see here in the upper right and the lower right quadrants of this particular slide. Now, when we talk about reflectivity, it's expressed in a unit that is not necessarily intuitive to us in our day-to-day lives. Reflectivity is measured in units of dBz, or decibels over Z. Now, we may know what decibels are. It's simply a unit of measurement, a logarithmic unit of measurement, I might add. And for those of us who are amateur radio operators, we know that a decibel is often referring to noise levels in signal strengths. For example, we may say that someone is 20 decibels over 5 and 9 if we're giving them a signal report and they're very, very strong. Or maybe we're doing weak signal work with the digital mode and we're listening to a signal that is negative 24 dB below the noise floor. We know what decibels are. They're simply a logarithmic expression of whatever we are trying to measure. Z is the unit that is being measured, and Z stands for the equivalent reflectivity factor of atmospheric objects, known as typically hydrometeors. And I realized that was a very technical definition, so let me break that down more clearly. What is the equivalent reflectivity factor? Well, that simply states that the radio wave that is being sent out from the radar is determining both the number and the size of hydrometeors in the atmosphere. Well, what is a hydrometeor? A hydrometeor is simply the meteorological term for objects consisting primarily of water that are suspended in the atmosphere. Hydrometeors simply refer to drops of rain, to hailstones, to flakes of snow, and so on and so forth. And the more hydrometeors, the more rain droplets, the more snowflakes, the more hailstones suspended in the atmosphere, the greater the number and also the larger the size. Raindrops and snowflakes can have various sizes. The stronger the reflected echo will be and the greater the dBz value. For example, let's think about a satellite dish. If you see a satellite dish atop someone's home, it's not typically particularly large. But if you see a satellite dish in a large satellite array, such as with NASA, they are utterly massive. Why? Because they're trying to amplify echoes from radio waves to make them stronger. The larger the size, the stronger the echo. And that's exactly what we see with increased sizing of hydrometeors. In other words, the bigger the raindrop, the larger the hailstone, the bigger the snowflake, the stronger and greater the reflectivity factor will be on radar. And radar expresses these dBz values visually in terms of colors. Now, typically, and I'll explain here why I don't recommend relying on colors or communicating primarily in colors over the air. Typically speaking, radar software, whether it be a free weather app on your smartphone that you downloaded from the App Store or from the Play Store, or maybe from another third-party app store, or whether you are watching your local weather station on TV or whatever it may be, radar typically will express dBz values of 50 in red, 65 dBz values in pink, and 75 dBz values in white. Now, I know that all sounds technical, especially for those who are just beginning their journey of understanding radar. To translate that, if you see red on radar, that generally will correspond to a value of 50 decibels over Z, or 50 dBz. Pink, 65 dBz, white, or hail cores as 75 dBz. Here's why I don't necessarily recommend that you refer to colors, however, over the air. As we now look at this larger image of radar reflectivity taken from Idaho. While it is true that many radar programs will use the same colors to represent the same values, many more advanced users will change these colors to fit their personal preference, and there are variations even between software as to the color themes that are used. So while it is generally true that the colors are the same. It's not always true. What may be red on my radar may not necessarily be red on your radar if you have your radar color schemes set up differently. And that's why I strongly encourage all trained SKYWARN amateur radio operators to always use the DBZ value rather than primarily the color. If we happen to use the color because we're so attuned to using colors on radars, that's fine, but nevertheless, we always, in my estimation, need to refer to the DBZ value so we know what intensity of the echo we are referring to. Here we can see that just north of this radar site, extending to the east and south of it, we can see that there is a large area of very light rainfall. In fact, while I don't have the temperature maps pulled up for this particular location, I believe actually that the grays and the blues, which would be DBZ values from 10 to 20 dBz up to about 30 dBz, were actually largely in the form of snow. And then as you approach the radar site, southwest of Idaho Falls in this particular screenshot, the precipitation, I believe, at this particular moment was transitioning more to rain, with the green values being 30 to 40 dBz and the yellow values being 40 to 50 dBz. But interestingly enough, just to the east of Power County, just to the southeast of American Falls, actually located in central Power County, in the state of Idaho, we actually can see some red on radars generated by GR level 3. But again, we don't want to refer exclusively to the color. We want to look at the corresponding scale that GR level 3 helpfully displays to us on the left side of the screen. And we can see that the small portion of red just to the southeast of American Falls is 50 dBz on radar. And doubtless some of you have heard me refer to intensifying convection on radar as exhibiting 50 dBz echo tops. 50 dBz and above is the range where you typically will start to see sub-severe, or depending on the strength of the overall storm system, severe impacts in terms of downdraft winds, in terms of small hail leading up to larger hail. You will often see more intense lightning in reflectivity values above 50 dBz. And so anything below 50 dBz, unless you have very strong velocity, which we will cover here shortly, you generally don't need to worry about, but there are always exceptions to every weather rule, of course. But once you start seeing values over 50 dBz that in GR level 3 are commonly expressed as red or pink or white, then you need to start paying attention because there may be sub-severe or severe impacts on the way. So just to wrap up our discussion here on reflectivity, reflectivity is very useful because it shows both the shape and the intensity of a storm or a collection of storms. And just to quickly run through the four most common types of storms, if you're not familiar, I have developed these further in other videos, and there are many resources that you can avail yourself of to study these more in depth. The four most common types of storms reflectivity will show you is a single cell storm, a multi-cell storm, a quasi-linear convective system, which sounds complicated, but simply means a somewhat straight line of storms, hence the name quasi-linear, somewhat straight, convective or storm system. Commonly a QLCS, simply the abbreviation for quasi-linear convective system, is more commonly referred to as squall line. Now, those of us in SKYWARN who happen to be weather nerds and so forth will still use the more technical phrasing, but in general public conversation, you will often hear them referred to as squall lines. Also, some of the most destructive storms are mesocyclones, or storms with rotation, with circulation within them, that are more again commonly referred to as supercells by the general public. And those are often the ones that spawn tornadoes, but not always. There are exceptions to that. And I would encourage you, if you're curious about diving into that topic further, to refer back to my Kent County tornado training videos that I have also publicly released on this YouTube channel. The final thing to understand about radar reflectivity is that it shows various elevations in degrees of tilt. And what do I mean by that? Well, a radar beam is focused in one particular direction, and the radar itself is typically encased inside a white outer shell. The radar beam begins horizontal, or at about a 0.5 degree base reflectivity tilt. As it spins in a 360-degree motion, it will continue to tilt more and more vertically over time. The maximum tilts on next-rad radars is 19.5 degrees to the best of my knowledge. Most radar software will only show you reflectivity from 0.5 degrees of elevation to 3.5 degrees of elevation, but you typically don't need anything above 3.5 degrees of elevation. If you're having some trouble grasping this concept of how a radar will tilt itself to direct the radar beam, think of taking a flashlight and standing in a dark room and beginning to just simply spin yourself in a circle. If you hold the flashlight straight out horizontally, obviously you'll be able to see anything that is horizontally in front of you. But as you continue to spin around and around, you slowly begin to lift the flashlight closer and closer above your head. Well, as you do so, provided you're looking at the beam itself, of course, you will see more and more of what is elevated above you, suspended above you. It's the exact same concept with a radar reflectivity tilt. It simply means the radar, as it is spinning in a circular motion, is tilting more and more vertically to look at storms or hydrometeors, rain, snow, hail, whatever the case may be, higher and higher up in elevation to get a better understanding of what is happening. So that covers radar reflectivity. Equally important, and in many cases even more so, is radar velocity. And now we're going to look at radar velocity, a less commonly issued product or rather I should say, a less commonly utilized radar product by the general public, but one that SKYWARN radar observers absolutely need to understand, particularly here in Kent County. Velocity simply is the speed at which atmospheric objects have moved since the last radar image. And we refer to radar images as volume scans, the scan of the objects in the atmosphere, the overall three-dimensional shape, in other words, the volume of them. And so it simply looks at where those objects in the atmosphere have moved since the last volume scan, and it can then calculate how fast they are moving. And so, for example, raindrops being transported by wind will show velocity signatures on radar, so we get an idea of how fast a storm is moving, for example. Units of velocity are commonly set to miles per hour or knots, but depending on what software you use, you also have other options as well, such as meters per second, and so on and so forth. Here in the United States, the National Weather Service will express velocities over water, such as over Lake Michigan, in knots, as that is a maritime unit of velocity, 1 knot equating to 1 nautical mile or 6,076 feet per hour, and velocities over land in miles or 5,280 feet per hour. So 1 knot is just over 1 mile. 1 knot per hour is just over 1 mile per hour. And for SKYWARN, I do recommend that you know how to use both. Generally, however, you won't necessarily need to refer to maritime velocities in knots because here in Kent County, we don't border Lake Michigan. So we do need to know what the equivalencies are, but we here directly in Kent County do not deal with mariners in contrast to what folks in our neighboring counties such as Muskegon, Allegan, and Ottawa counties would. But nevertheless, the maritime warnings that are issued by the National Weather Service are very useful because often if it's happening over water, it's going to happen over land as well. So I personally prefer to use miles per hour and convert knots to miles per hour as we don't border Lake Michigan here, but nevertheless, we are within a half hour to 45 minutes drive of it, of course. So 34 knots is equivalent to 40 miles per hour, which is below severe limits. 40 knots is equivalent to approximately 46 miles per hour, again below severe limits, but there would be potential for isolated severe gusts in a storm system producing sustained 40-knot velocities. And finally, 50 knots, which is equivalent to 57 miles per hour, which is basically severe criteria for a land-based product. A special marine warning with 50 knots is generally equivalent to a severe thunderstorm warning because of wind speeds about 60 miles per hour or greater being possible over land. But as we look at these velocity images on the right portion of the slide here, we see that they are expressed in greens and blues only. In some cases, you'll actually see more colors than that if there are really extreme ends of the spectrum. But generally, you will see greens and reds. I may have misspoke earlier. Generally, you will see greens and reds with velocities. But again, this can also vary depending on what color scheme you have personally set. So, velocities moving toward the radar site are green, known as the inbound velocities. And they're expressed in negative units, not because they are actually negative in real life, but simply because they are moving towards the radar. So a storm system that's moving towards the radar would be shown in green and expressed in negative units of velocity, such as negative 25 miles per hour. Once it passes the radar site and moves away from the radar site, it's expressed as outbound velocity, in other words, outbound from the radar, and is expressed in positive units, such as 25 miles per hour. Again, negative and positive units mean exactly the same speeds. It simply is referring to the direction the wind is coming from and the direction that the wind is going. And the reason why interpreting velocity signatures just being synonymous with the image that velocity products show us, the reason why it's so important is because, especially for Kent County weather, with embedded spin up tornadoes and squall lines, velocity signatures often will reveal more to us than reflectivity signatures will. So I would strongly encourage folks to spend as much time as they are able and interested in studying velocity signatures in depth. So here's a relatively simple image from Salt Lake City, Utah of velocity signatures. We can see that the wind is green on the left side of the radar, so we can look at our corresponding scale in GR level 3, and we can see that green is expressed in negative units, so we know that the negative wind speeds refer to wind that is moving towards the radar. Yeah, here in this particular instance in Salt Lake City. So we know that the wind is moving from the west, and if we estimate the colors on radar with the corresponding scale, in some cases the wind is moving anywhere from about 10 to 30 miles per hour from the west. Once it moves directly away from the radar, it's again the exact same wind speed and the same storm system, but it's simply expressed in outbound velocities here in GR level 3 in red because it's moving east away from the radar. So that is a basic introduction of reflectivity and velocity. And now, as we approach the live demo of GR Level 3, where I will take you through recommended setup procedures, let's just very quickly, ahead of that, look at common radar software today. And I will develop this further in subsequent videos for those who are interested. There are some consideration factors that you need to take into account, such as the overall cost, the scalability, in other words, how many devices will it work on? Will it only work on one device? Will it only work on a computer? Will it work on your computer as well as your phone? Will it only work on an iPhone? Will it also work on an Android as well? That's what I mean by the term scalability. The hardware requirements. Some radar softwares are more graphics intensive and require more optimized graphics cards than others do, as well as bonus features, especially if you are into forecasting or if you are into things such as hurricanes and so forth, which I am as a member of the Salvation Army Team Emergency Radio Network. There's just a list of factors that we need to consider when we select radar programs for our analysis. Some of the most common ones would be Radar Omega, Radar Scope, WSV3, and of course, the recommended one here in Kent County, Michigan, from our SKYWARN team, is GR Level 3. The other softwares I won't touch on right now. I highly recommend that you get those if you are interested and able, but nevertheless, that will be the topic for another training class in another video. So as we look at GR Level 3 software, we see that it can be purchased from grlevelx.com. Phonetically, that is Golf Romeo Lima Echo Victor Echo Lima X-ray.com. There's 3 different softwares that you can purchase, however, so just make sure you're purchasing the right one. And again, all of these you can trial for free, I believe, for approximately 21 days or 3 weeks. The one that we use, and the one that I will demo here very shortly, is GR Level 3, version 2. Not GR Level 2, but the second edition of GR Level 3. This has a one-time purchase price of $79.95, and provided you write down your license key, which I strongly recommend that you do, you will be able to install this on as many computers, whether desktop or laptop, as you are able. It does not work on a mobile phone, but it does work on a computer. There is a more expensive cousin, however, to GR Level 3, and that is GR2 Analyst, and that has a one-time fee of $250. Now, the advantage of GR2 Analyst is that it does what is known as volumetric rendering of reflectivity, which is simply a fancy way to say that it does 3D modeling of storms, which is very, very interesting to those who have both the interest and the budget to afford a $250 purchase price, but it's not necessary in order to be a radar analyst for Kent County SKYWARN. And finally, software that was good back in its day, but I no longer recommend, is GR Earth, which was used for national and international radar. This one costs $180 per year as a subscription, and there are frankly much cheaper radar programs on the market now that actually will outcompete GR Earth at this point. But GR Level 3 for a one-time fee of $79.95 as of this recording date of January 19th, 2023 is what we recommend, and it is certainly well worth the investment. So at this particular point in time, I am now going to exit away from the slide deck, and I am going to pull up GR Level 3. And we're going to spend the remainder of our class together looking at recommended setup options for GR Level 3. Now, if you've purchased GR Level 3 and you're opening it up for the first time, you may not see all of these options right away. So let's discuss the basic interface of GR Level 3. So we can see here that we've got our main radar in the central window. Down here in the lower right-hand corner of the screen, we can see that it's showing us data. It's showing us the degree in terms of a 360-degree circle on radar. It's showing us the DBZ value. In other words, for example, if I hover my cursor over the yellowish orange region of rainfall to the west of Van Buren County, currently over Lake Michigan, I can see that that color corresponds to 45 dBz. And again, the 45 dBz value is what I would actually report on air, not necessarily the color. But we can also see next to the dBz value in the lower right corner on the bottom toolbar that it's showing me that it's reading 45 dBz values of reflectivity at an elevation of 5,770 feet. And it also is showing me the GPS coordinates in decimal degrees as well. And so that is the basic structure of GR Level 3. Again, we've got our color scales here on the right, which is very, very useful. Down here at the bottom left-hand corner, we can see, perhaps not all too clearly in this particular image, but nevertheless we can see what elevation we are looking at in terms of our radar. Here we can see a base reflectivity of 0.5 degrees of tilt, and we'll get into here shortly how you can set various degrees of tilt for various products. As we move along the upper toolbar right here, you've got a series of icons that all do various things. If you want to look at past radar images, you can click Download Recent Data, the Pages icon, or the Sheets icon. If for whatever reason you wanted to stop pulling in radar data, you could click the globe with the computer and the red X to stop pulling the data. Here, you've got your navigational buttons. You've got the buttons to go back to the oldest volume scan on radar. Here, as you can see, I've moved the radar image back to the oldest scan that it still has downloaded. If I want, I can then jump ahead to the most recent scan as well. Let's say, however, I only want to go back one scan at a time. I can click the previous volume scan and just manually loop the radar back and forth as I see fit. Or I can also click the play button and I can watch the classic radar loop that we are familiar with when we observe radar in our general day-to-day lives. Here, We can see the magnification options as well as the ability to reset the magnification. Obviously, of course, if you've got a scroll wheel on your mouse, you can use that as well. But nevertheless, you can use the magnification buttons, the icons up here on your toolbar if need be. If we want to zoom all the way back out, obviously we can hit the zoom none button. The smoothing button, I do recommend that. As you can see, GR Level 3 will smooth the reflectivity values so they're not as pixelated. It is visually more appealing and much cleaner and does aid in better radar interpretation, in my opinion. Now, if we wanted to, for whatever reason, although I don't recommend it, if we unchecked the Show Radar Data button, then we would no longer see anything on radar. So that button, in a practical sense, is of no use. Here we can show the melting layer. I personally do not use this feature. You can do so if you wish. But one thing I do recommend, and here I will zoom into radar a little bit more so that way you can see it, especially if you're viewing this video on a smaller screen. Let's look at these white lines with these demarcations at regular intervals in there. These are what are known as storm tracks. And here I will toggle them off and then back on so you can see them. What these do is demonstrate two things. Firstly, they show the direction that the storm is moving toward. And secondly, each hash mark, each demarcation on this line, represents 15-minute increments based on how fast the storm is moving per radar. So, for example, this particular rain shower right here, that is currently just to the southwest of Plainwell along the US 131 and I-94 corridors in Kalamazoo County, we can see that it is going to move into downtown Kalamazoo in approximately, if we look at this particular line right here, we see it's half of a 15-minute interval. Downtown Kalamazoo is going to get moderate to light rainfall in approximately 7.5 minutes based on current radar trends. And actually, if we look at the latest volume scan, we can see that the rain showers have actually indeed moved well beyond downtown Kalamazoo when we update the radar. But nevertheless, that for demonstration purposes, you could determine if that were a live radar image, how quickly a storm system would move into a particular area, or snow or rain showers, or whatever the form of hydrometeors might be in that particular case. Here you can toggle hail icons on and off. Right now, being winter, there are no hail icons embedded within this system, but I do recommend that. It will tell you the percentage and the estimated size of hail within updrafts. NMD icons, we're going to cover that. That is a technology that GR Level 3 uses to try and detect circulation that may lead to tornadoes. But that is what NMD stands for. New Mesocyclonic Detection, I believe, is the full term. Here, I do absolutely recommend that you do have this toggled on. Show TVS icons, tornado vortex signatures. Again, just another way for software to alert you to the presence of possible what is known as updraft helicity, which simply means rotation spiraling upward within a storm, circulation spiraling upward within a storm, which could produce vertical rotation, obviously in the form of a wall cloud, funnel cloud, or tornado on the ground. Here, if we want, we can toggle LSR icons on and off with the orange polygon. I don't believe that I've got that enabled right now. We can also see the precipitation type if we are interested, and this is useful. So here, for example, we can see that everything south of the I-96 corridor, this red line, this I-96 corridor in Ottawa, Kent, and Ionia counties is rain, and it determines that by the temperature data. And here in Muskegon County to the northeastern portion of Allegan County, we've got a mixture of rain and snow possibly as well. Again, so light it's probably not really impacting travel or anything like that. But we can see that due to the temperature, we can see what the overall precipitation type will be. Actually, although I don't have it displayed here, there are winter weather advisories in these northern counties in lower Michigan because this warm, moist air, which is currently producing rain showers in southwestern lower Michigan, as it continues to move to the northeast, will get colder and then will change form into potentially light freezing rain as well as some snow. So that is useful, although I don't recommend that you have that toggled on all the time because then you won't be able to see the reflectivity factors all that well. And now we can proceed to looking at these menus. And we're not going to cover all of these menus this evening. We're only going to cover the features that show basic setup to get you up and running with GR Level 3. I will, however, over a series of subsequent videos, thoroughly cover all of these options in more detail for GR Level 3. So let's begin first of all. We're going to start with this third menu here and look at the site. So if we click on the site menu and we click on settings, we need to change the startup site to KGRR, or the National Weather Service radar site here in Grand Rapids, Michigan. And also ensure that automatically connected startup is selected, so that way it brings you to the Grand Rapids radar every time. Now, obviously, this is for Kent County residents who participate in SKYWARN, or actually any surrounding residents of West Michigan counties. But let's say you don't live in Kent County or in Michigan. You can set the radar to whatever is closest to you, and I strongly recommend you do that. So let's say, for example, you live in Chicago. What you can do if you're not certain what the startup site code is, the 4-character code for your radar site, what you can do is you can click change, and then you can just start scrolling by state and then by city in alphabetical order, of course. So let's say that we live in Chicago. Well, we obviously know Chicago is in the state of Illinois, so first we need to find the state, and then of course we can find the city of Chicago. And I'm not going to go ahead and change it right now because I'm not a resident of the city of Chicago, but that's how you would do it if indeed you were. But I also do recommend that you add surrounding radar sites in your favorite sites menu right here. As you can see, I've got various surrounding radar sites to the Grand Rapids radar site added as favorites, but when you open up GR Level 3 for the first time after trialing it or purchasing it, this will be empty. To add them, you just click the Add button, and again, you just want to start with your own local radar, and then just do a little bit of research to see what the surrounding radar locations are. The value in that is that if I exit out of this dialog box, or rather this screen, and I go to site, now I can see all of my favorite radar locations very easily accessible. So if I want to see what's happening, for example, in Milwaukee, which is a radar site we will frequently refer to as storms in the northern hemisphere generally move from the left to the right due to the cyclonic rotation and the cyclonic wind streams and so forth in the atmosphere. But let's say I want to look at Milwaukee. I can just easily select Milwaukee because I've got it loaded as a favorite. And I can see that they've got some rain showers, and actually, as I think of the thermal gradients, or in other words, the temperatures over in Milwaukee right now, it's very likely actually in the form of snow and not in the form of rain, as they are on the colder portion of this particular precipitation system this particular evening. But nevertheless, I can quickly pull up Milwaukee radar, and I can see what's going on in Milwaukee. Let's say I want to look at Chicago, another very frequent radar site that we will observe in our Kent County SKYWARN operations. I can just click on Chicago if I have it saved as a favorite, and I can see that Chicago doesn't really have any remarkable precipitation to speak of at this time, other than some light drizzle, perhaps in the form of some very, very light snow at this particular moment in time. But let's say I don't have those added as a favorite. What you can also do as well is you can just navigate around the map, and you can just click on radar locations in order to pull them up. And so I can just continue to navigate west. Let's say I want to look at radar in Minneapolis-St. Paul, in the Minneapolis-St. Paul Metroplex. Then I can look at radar here, and I can see that there's nothing in the city of Minneapolis-St. Paul right now, but there is some light precipitation to the due southwest, due south, and due southeast of the Twin Cities. And now I just want to navigate back, but you'll notice now I can no longer click on our native radar here in Grand Rapids because I've gone too far west. Well, not to worry, I can go back to site, and I can just click on KGRR for Grand Rapids, Michigan, and pull up our hometown radar again. So that covers the site options. Let's now actually go to back a menu and go to view. And I purposely picked site first because when you initially purchase it, it will not be loaded with your native radar site, and you'll need to set that first. But let's now examine some options we've got with zoom. If you wanted to, you could click zoom in, zoom out, and zoom down, which is simply a repetition of the magnification options along this toolbar, or if you have a scroll wheel, which pretty much all mice do these days, you don't even need to use the menu options to do so. But let's go to view. One thing, this is completely personal preference, and I would say if you are relaying information to emergency management, do not have this enabled because it's always best, as a general rule, to use local time when interfacing with emergency management, not Zulu time. Although if you're talking to the National Weather Service, using Zulu time, that is universal time, is perfectly acceptable because that's what they use. You can check or uncheck the universal time option. So for example, when I have it unchecked, you can see in the upper right corner of the central radar window that the local time here as I am talking is 12:17 a.m. on January 19th of 2023. But because most weather products don't operate in local time, they operate in universal time, I want to check show Z time again, and it converts it to universal time, which is 0517 hours or 5:17 a.m. universal time. But that is a feature that is personal preference. Now let's go back to view and click on animation settings. And here I can determine how much radar data I want to save and also how fast that I want it to operate. So let me go ahead to demonstrate this. Go ahead and click play, and you can see the current speed that I have radar set at right now. I'll zoom in a little bit to make it a little bit more distinct. I click view, I click animation settings in the view menu. Let's say I just want to speed it up. I can speed it up very rapidly. This would be too rapid actually for any practical use. Or I can slow it all the way down to be very, very slow. And you don't generally need it this slow, but there are times where you will need to very carefully pick apart radar frame by frame or volume scan by volume scan. And so you may want to set it this slow. It's personal preference, and it's up to you. So let me go ahead and clear that out because I've got it set where I like it. Let's go back to view. Let's go to NMD filter settings. And this is one of the more important settings that I do recommend that you set exactly as I've shown here because I did not come up with these. This is the recommendation per Ernie Asuno, a local meteorologist here from the National Weather Service in Grand Rapids, Michigan. And this refers to the NMD filter settings, or the ability for GR Level 3 to display rotational icons if it suspects or thinks it sees any rotation on radar. Make sure that your max base is set to 5. Again, you can toggle it from 0 all the way up to 20,000. We need to set it to 5 per the guidance from our local meteorologists in the National Weather Service. And the minimum depth needs to be 8. This is to cut down on false positives on radar where it may indicate circulation where in fact there is none. I will liken this feature to a ham radio analogy in that this option from GR Level 3, which you will not find in other programs, it's native only to GR Level 3, is synonymous with computer generated Morse code. If a computer is hearing another computer generate Morse code, that computer will be able to perfectly copy that Morse code. But as soon as you add in human deviations in sending Morse code, a computer, no matter how good it is, even in the year 2023, will get confused very, very quickly as to what dits and what dots are being sent, and it will start to scramble the message very, very fast. In my opinion, NMD filter icons function in the same way. That when the velocity scans are clean, when they are textbook, when they are relatively easy to interpret, when there's enough time for the software to interpret them on its own, it will generate icons appropriately. But there are other times, especially when radar becomes contaminated, where it either will not generate them when it should, and there actually have been several instances throughout the 20-year history of tornadoes in this millennium here in Kent County where it has failed to demonstrate them when tornadoes were on the ground. But I have also seen during active SKYWARN activations where it has falsely generated these NMD icons when there was nothing on reflectivity and also nothing in terms of surface observations as confirmed by trained SKYWARN spotters. So just take it for what it's worth, use it. It's helpful when you're first learning radar, but don't ride or die based on it. And just make sure that when you see it, you engage it with curiosity to see why it's being generated, but don't rely on that solely for indicating whether a potential mesocyclone, that is a supercell, which may or may not spawn a tornado, actually exists. So just a word of advice for that. Now, let's go back to the View menu, and we'll click on Warning Settings. You will have two different options to choose from. It will by default be set on GR colors. I would recommend you use NWS or National Weather Service colors. And as I continue to talk and demonstrate these, I'll just constantly toggle these back and forth. And you can see that the only two colors that are changing are the thunderstorm product and the tornado reported product. The tornado reported product simply makes the outline of the pink of the black bars above and below the pink lines thicker. That doesn't matter at all. That's fine. But the thunderstorm product in GR default colors is in red, whereas the National Weather Service will always use yellow and not red. They will always use red for tornadoes and not for thunderstorms. And you can see here GR colors actually will change tornado warnings always to pink. The National Weather Service will always use red for tornadoes that are not yet confirmed to be on the ground but are nevertheless warned because of the potential. As soon as a tornado is confirmed on the ground, however, the National Weather Service will issue pink polygons and not red ones. And it keeps the severe thunderstorms separate from the tornadoes by issuing yellow polygons rather than red ones. So I recommend that one of the immediate changes you make is switching to NWS colors rather than GR colors. The problem is it can generate confusion, especially if you are using multiple radars and other people, if you say, hey, I see the red warning polygon for Kent County, people are going to assume, as most people will run the National Weather Service colors and not the program default colors, oh no, red means a tornado warning, when in reality, it's just the custom GR color for that particular product. So I recommend use the National Weather Service colors, and it will help ensure that operations go smoothly. And now I will just demonstrate two other menus here as we draw to a conclusion. One is the GIS menu, and this, I have all of mine selected right now, but when you load GR Level 3, and if you've been watching and following along, you're probably wondering why your radar still doesn't quite look like mine, and that is because of the GIS menu. So let me go ahead and uncheck all of these, and you will be able to see what each of them do. So as I continue to uncheck all of these, you can see that more and more detail is being uh, taken away from the map. By default, the show base states will probably already be selected, but the stock setup for GR Level 3 will probably look like this. It's somewhat useful, but not all that much, in my honest assessment. So let's first go ahead and we need to see where the counties are, because something that's happening in Ottawa County is certainly relevant to Kent County, yet nevertheless it's not actually occurring yet inside Kent County. So let's go ahead and enable our county lines by going to the GIS menu and selecting Show Base Counties. And now that's a better level of detail. We can see Kent County here, and we can see Ottawa County to our due west, Muskegon County, Newego County, Montcalm County, Ionia County, Berry County, and Allegan County. But you may ask yourself, wait, how do you know that those are actually the counties? Well, I know them from experience, but in the event that I didn't, I can go ahead and I can also select Show County Names as well, and now I can see all of the county names. And I recommend that regardless of how well you know your surrounding counties, you always have county names enabled. But I also need to know where population centers are. So let's go ahead and click Show City Names. And now I can see city names italicized here, and as I zoom in, I'll be able to see more population centers. Here I can see the city of Grand Rapids, I can see Wyoming, I can see Kentwood, Cutlerville, Byron Center, and so on and so forth throughout the county. When we get to the level of county detail, it's very helpful to refer to the nearest population center such as Grand Rapids, East Grand Rapids, Granville, Kentwood, Forest Hills, Northview, whatever the case may be, when relaying weather reports over the air, especially with radar analysis and observation. So, one other thing that I recommend as well is to have the radar sight enabled, and that just shows you it's a little bit visually easier to see when you can see the radar code as well, especially if you're more zoomed out. They just visually pop a little bit better. And it also will get you accustomed to how the National Weather Service refers to its individual radar sites. Here in Grand Rapids, KGRR, but if we look at Chicago, KLOT, for example. So moving back to the KGRR radar, the other final thing that I would recommend you set up, and this is personal preference, but I would nevertheless encourage you to do so, is to show the background. And that will load satellite imagery. And what this will do is it will show you terrain features. And that will give you an even better idea of where storm features are in relationship to your local geography. Here, for example, we can see the river basin of the Grand River as it makes its way to the north and eventually the south of Grand Rapids in that horseshoe bend along Grand Rapids and Comstock Park before it terminates at Northview, not in terms of river flow, but in terms of the apex of the horseshoe shape, and then comes back down in a southerly direction through the Plainfield Township areas and then through Forest Hills before it then moves east towards Lowell, Saranac, and then obviously Ionia and later on Lansing as well. But also you can see the major roadways as well too. I will say GR Level 3 unfortunately does not include highway or interstate labels. So when using GR Level 3, you do have to know those, you do kind of have to memorize which ones those are. But if you've been a resident for any length of time, then you will probably intuitively know which major roads are which. But I also need to see these roads better visually, so I'll go back to the GIS menu and click Show Base Roads. And GR Level 3 does have a color scheme. You'll notice different color schemes for various roads. Interstates are in these dark red lines. U.S. highways are in these orange lines. County roads, or rather state highways, are in these yellow lines. County roads are in these thinner yellow lines here. And I realize if you are audibly listening to this presentation, that's not necessarily all that helpful, but nevertheless, for those who are watching the presentation on YouTube, you will be able to see that there is indeed a color scheme and there is a method to the madness here in GR Level 3. So for example, US highways, this is US 31, this is US 131, and this is US 127. This is Interstate 96 or I-96 as we refer to it here. This interstate beginning in central Grand Rapids, or rather beginning just north of East Grand Rapids and then moving to the southwest, this is Interstate I-196, not to be confused with Interstate I-96. And I realize that I'm using a tautology, which is just a technical phrase for I'm being repetitive when I say Interstate I-96. It would be more accurate just to say Interstate 96. But nevertheless, it's very helpful when referring to storm systems to refer to major highways as well. The National Weather Service will do this, in fact. So here, for example, we can see in this particular radar image that we've got rainfall occurring in Muskegon County along the US 31 corridor that is to the north of Norton Shores and just south of Rothbury in Oceana County. We don't have anything significant in the main US 131 corridor or the I-96 corridor, but nevertheless, we do have some precipitation occurring in Allegan County along the Interstate 196 corridor, as well as some heavier precipitation to the immediate east of the US 131 corridor and south of the I-94 corridor in Kalamazoo counties. So those are why I would recommend that you use roadways to refer to anchor points in your radar. And the final thing that I will look at here with you are the panel options. And in looking at these panel options, we can see that we've got an option for a single panel view, a dual panel view, and finally a quad or a 4-panel view. And each of these can be saved as individual favorites as you see fit. I will generally run this particular quad panel view all the time with base reflectivity, composite reflectivity, base velocity, and correlation coefficient. But as you start out, I recommend that you run a dual panel view and you have reflectivity on the left and velocity on the right. And we'll get into much more detail as to what products you can use, and we'll experiment with panel views and so on and so forth in subsequent videos. But that covers the live demo of GR Level 3. And that also concludes our live training for Kent County SKYWARN Basic Radar Training. I hope you enjoyed it. If you have questions, certainly feel free to leave them in the comments below. If you would rather not leave a public comment on YouTube, simply look up my email on qrz.com. If you are a ham radio operator, then you will certainly know how to do that. And just email me directly. And I hope to see all of you again in subsequent radar training videos for Kent County SKYWARN. With that, as a ham radio operator, I will say 73, and I will be clear.